In this session, we will introduce the concept of homomorphic transformation and the definition of cepstrum and complex cepstrum. Homomorphic transformation generally refers to making the nonlinear combination signal into a linear combination signal through a certain transformation, so that it can be more convenient to use a linear operation to process the signal. As is shown in the equations, homomorphic transformation converts convolution operation into additive operation and corresponds to the characteristic system. Complex cepstrum and cepstrum are homomorphic transformation, which can help us separate sound sources and channel filters. We can use a convolutional characteristic system to describe the computation of complex cepstrum. There are two kinds of definitions, including complex cepstrum and real cepstrum. The complex cepstrum refers to the inverse Fourier transform of the logarithm of the Fourier transform of a function. It does not mean a complex signal, but a complex logarithm is applied. Cepstrum is defined as the inverse log Fourier transform of the short-time amplitude spectrum or power spectrum of the signal. The complex cepstrum is a complex logarithmic operation, while the cepstrum is a real logarithmic operation lacking phase information. Spectrum is Fourier transform of signal autocorrelation. Spectral analysis is also called frequency analysis. Cepstrum is the results of taking the inverse discrete Fourier transform, IDFT, of the logarithm of the estimated spectrum of a signal. The name cepstrum was derived by reversing the first four letters of spectrum. Operations on cepstrum are labeled frequency analysis, Lifting, or cepstral analysis. If the signal Xn is a real signal, then its real cepstrum and complex cepstrum are also real signals. The real cepstrum is the even part of the complex cepstrum. Generally speaking, we can call real cepstrum as cepstrum. Let us investigate the similarities and differences between complex cepstrum and cepstrum. They have a similar definition and relations. The convolution signal can be converted to additive signals through complex cepstrum or cepstral analysis. After a signal sequence is transformed by the characteristic system and its inverse system, the complex cepstrum can restore the original signal information, while cepstrum cannot, because the computation of real cepstrum lacks phase information. Nevertheless, cepstrum can still be used in speech signal analysis, because human hearing perception of speech is mainly contained in amplitude information, and phase information does not play a major role. The results of complex cepstrum and cepstrum computation lead to a sequence in frequency domain, which has the unit of time. Figure A shows the complex cepstrum of synthetic speech. Figure B shows the cepstrum of synthetic speech. Both real spectrum and complex spectrum are bilateral decay sequences, and the energy is concentrated near the original point, which is why it can be approximated with a limited number of coefficients. Therefore, people regard the truncated spectrum signal as the spectrum vector. For voiced speech, there are obvious peaks in frequency domain. The following figures are the results of spectrum and complex spectrum analysis on the 4 speech signals are the st. Most speech recognition systems use the spectral coefficients of speech signal to describe the frequency spectrum, because the spectral coefficients have good distinguishing characteristics between different phonemes and are generally independent of each other. And for a specific phoneme, the spectral coefficients are approximately Gaussian distribution. The analogous speech signal can be generated by the convolutional combination of glottal excitation signal Pn and vocal tract function Hn. The sequence Pn is minimal phase and Hn is mixed phase, zeros inside and poles outside the unit circle. We could compute the complex spectrum of Pn and An to get the results Pz and Hz. Spectrum is the Fourier transform of the logarithm of speech spectrum and can be used to separate vocal tract information from pitch excitation in voiced speech. The figure here shows the complex spectrum of analogous speech signal Xn equals Pn convoluted with Hn. The horizontal axis is frequency, which has time significance. For a finite length periodic pulse sequence, its complex spectrum is also a periodic pulse sequence of the same period. Linear prediction separator coefficient, LPCC, is the representation of linear prediction coefficient in the spectrum domain. This feature is based on the assumption that speech signal is an autoaggressive signal, and spectral coefficient can be obtained by linear prediction analysis. Thus, LPCC reflects the characteristics of vocal channel. It should be noted that we cannot use spectrum coefficients to inverse LPC coefficients, which will cause system instability. LPCC discards the excitation information in the signal generation process, and more than 10 spectral coefficients can represent the characteristics of the format. So, LPCC has good performance when applied in speech recognition. In speech processing, the male frequency spectrum, MFC, is a representation of the short-time power spectrum of a sound, based on the linear cosine transform of a log power spectrum on the nonlinear male scale of frequency. Male frequency spectral coefficients, MFCC, are coefficients that collectively make up an male frequency spectrum. Taking into account the characteristics of human hearing, the linear spectrum is first mapped to the male nonlinear spectrum based on auditory perception, and then converted to the cepstrum. The difference between the cepstrum and the male frequency cepstrum is that in the MFC, the frequency bands are equally spaced on the male scale, which approximates the human auditory system response more closely than the linear spaced frequency bands used in the normal cepstrum. MFCC are commonly derived as follows. Take the Fourier transform of a windowed export of a signal. Map the powers of the spectrum obtained above onto the male scale using triangular overlapping window. Take the logs of the powers at each of the male frequencies. Take the discrete cosine transform of the list of male log powers, as if it was a signal. The MFCC are the amplitudes of the resulting spectrum. Male frequency cepstrum coefficients are most popular features extracted from speech signals for use in recognition tasks. That's all for this session. See you next session.